Let's say you're asked to graph the equation y is equal to 1/3 sine of 2x minus pi over 2. In order to graph this out, we're going to take this piece by piece, and our steps are going to be the following. So we want to do it by hand, and we want to take the inside piece right here, because that's the part that happens to the x variable first. Okay, so the first thing to happen to the x variable is the 2. Okay, so that's the first thing. And the second thing on the inside of the parentheses, the second thing to happen to the x is the pi over 2. Then after those two things impact the x, then the sine function has a chance to work on the variable. So what I'm going to do is I'm going to graph this out in stages. And so the first thing I'm going to do is recognize the parent graph. Now these you need to have memorized. Okay, our parent graph, or our parent function, is the sine function. So the first thing I want to do is graph out what is y is equal to sine x. What does that guy look like? So we need a good sketch of it. What I'm going to do is I'm going to graph from negative pi to 2 pi. So let's go 1, 2, 3, 4. 1, 2. Now you can scale however you want to. This is our x-axis. This is our y-axis. Here's -1. Here's +1. And so I'm going to count by pi over 2. So here's pi over 2. Here's pi. 3 pi over 2. 2 pi. So here's negative pi over 2 and negative pi. Now these values we can get easily off the unit circle. So let's go ahead and graph this guy out in purple. So the sine at 0 radians, well there's 0 height there, so it's right here. At pi over 2, the sine value is 1. At pi, the height value is 0. Then back down and back up again. And again, you can verify all of these values on the unit circle. And so the function looks like this. And don't draw straight lines between, guys, because it's nice and curved like this. So I've seen some people drawing straight lines in between. Don't do that. Okay. So this purple line, of course it continues up like this. Okay, it continues up like this. This purple line is the sine function, so this is sine x. Okay, now what we're going to do is we're going to step by step graph each of these pieces. So the first thing that happens to the x is the 2, the second thing is the pi over 2, and the third thing is the 1/3. Now when you're acting inside the parentheses, in here, everything has the reverse or the opposite effect. So since we're working in reverse, the first thing to happen to it is this 2, and the second thing is the pi over 2. But we're going to work on the pi over 2 first because we're working in reverse. So the question is, what happens, what does this guy do to the sine function? So let's go ahead and put that guy into motion. So we've got y is equal to the sine of x minus pi over 2. So let's see what that does to the curve. So we're going to go ahead and just redraw out as best we can here. So here's our x. Now, the purple is sine x. By putting a minus pi over 2, we do the opposites of what we see here. So we're really thinking about adding or moving to the right by pi over 2. So whenever you add or subtract, that is a shift of the entire graph to the right or the left. Adding and subtracting means we take the whole graph and slide it. Multiplication or division means we take it and compress it or stretch it. So this guy is going to move everything to the right by pi over 2. So let's go ahead and mark out our values that were. Now you can put these graphs over top one another, but the problem is you end up making kind of a mess. And so every point moves to the right by pi over 2. So this point right here that was at pi over 2 up at a height of 1, this guy right here, we now add pi over 2 to this. So we can think about it like we add pi over 2. Now the height value still stays the same. So this guy moves to the right by pi over 2. So it will now end up at a point, pi over 2 plus pi over 2 is pi, which is this guy, and up at a height of 1. So pi up at a height of 1 is a point on my new curve. Now this guy moves to the right by pi over 2, so it moves this way. So what was normally, and I'll draw my original function just so you can see it. Okay, again, here's the original function. The purple one is sine x. And now what we're doing is we have this movement to the right of every single point by pi over 2. And so, if we connect the dots, what we've got here is a shift of movement to the right by pi over 2. So I'm going to erase the purple line here now. We'll get that back in a second. And this new yellow graph, is this function right here. Okay? That's all it is. So the yellow curve is this graph. Now we'll work on the next piece. Well, we work in reverse on the inside. So we already dealt with this guy. Now let's put this guy in the mix with all this. So what we want to graph out now is y is equal to the sine of 2x minus pi over 2. Okay, so again, we'll graph out our system here. Here's x. Okay. Here's negative pi over 2, pi over 2, pi, 3 pi over 2, 2 pi, so on and so forth. Now the difference between the yellow line and the green line is this 2. What this 2 does is it changes this yellow function, and normally when we multiply or divide, we think about that as a stretch or a compression, stretch or shrink. Because it's happening on the inside, that means it's a horizontal stretch or a shrink. Okay, so multiplying on the inside of the parentheses means horizontal stretch or shrink. Okay, and we always work in the opposites of what we see only on the inside. So this 2, because this multiplication is a stretch or a shrink, Normally we think about multiplying something by 2 as making it larger, but this will actually make it smaller because it's the opposite. So things are going to happen twice as fast. Things are going to push, it's going to compress or shrink horizontally by a factor of 2. So anything that happened at pi will now happen at half of that. So watch, I'm going to graph the yellow one. We'll put the yellow graph in here. Again, I'm trying to make it nice and smooth. That's what it would look like. Now, everything's going to happen twice as fast, meaning that a point that normally happened at pi over 2 right here is going to happen at pi over 4. So this point got moved back. A point that would happen at pi happens in half of the time. So if it normally would happen at pi, this point now happens at pi over 2. So notice that this guy only moved back by pi over 4, but this guy moved back by pi over 2. The further it is away, the more it'll move back. So this guy that happens at 3 pi over 2 now happens at half that distance. Think about it as 3 pi over 2 multiplied by a half. That happens at 3 pi over 4. Just like if I took pi over 2 and I multiplied it by a half, that happens at pi over 4. And if I took pi and multiplied it by a half, that's pi over 2. So that's where we're getting all these from. So 3 pi over 2 happens now at 3 pi over 4, which is right about here. So this guy moves back to here. The guy that normally happened at 2 pi now happens just at pi, so this guy moves back to here. The guy that happens at 0, well, if we do the math out over here, okay, let me delete this so we have some more room. 0 multiplied by a half, well, that's still 0, so this guy stays where it is. Negative pi over 2 multiplied by a half. The reason we're multiplying by half is because we're doing the opposite of multiplying by 2. It's the opposite of multiplying by 2 because we're working on the inside again, guys. It's opposite. So multiplying by 2, we're multiplying by a half. If there was a 3 here, we'd multiply by 1/3. If there was a 10 here, by 1/10. If there was a 1/5 here, by 5. Multiply by the reciprocal. So this guy moves to negative pi over 4. And this guy moves to negative pi over 2. Okay, this guy right here would move in to about right here. So if we draw it out, it looks like that. So what we've done is we've compressed in this. Notice that the points, as we got further and further away, the compression lines here got larger and larger. They moved in further and further. Okay, so the further a point is away, the more this guy impacts it. So now what we've got, if we erase the yellow curve and get rid of some of these lines in here to get rid of the mess, oops, that's the one I wanted. This new green line is this right here. So if I took a graphing program or calculator and I graphed this guy out, this is what it would look like, this green line. Now we're almost done. We've got most of the function. Let's go back up and see what we're missing. We're missing this 1/3 out front. So let's graph that guy now. So we'll do that one in blue. Y is equal to, see how I'm building each time I'm building on the previous function. The first time, I put in the negative pi over 2. The second time, I put in the 2. The third time now, I'm going to put in this 1/3, so on and so forth. You just keep adding the pieces. You start on the inside, working in reverse, and then you go to the outside. And you work in the normal pattern on the outside. Everything on the outside happens exactly like you think it would. So here's negative pi. Here's negative pi over 2. Pi over 2. Pi. 3 pi over 2. 2 pi. Now I'm going to graph out, I'll regraph out the green guy. So the guy from the last one here. Of course, it keeps going on, right? I could continue on this way, I could continue back down this way, so on and so forth. So the green guy is this, up here. The blue guy now, what we added to it was this multiplication of 1/3. And again, we multiply or divide. Anytime we multiply or divide, it is a stretch or a shrink. Because it's happening after sign has occurred, it's happening outside of the function occurring, then it is a vertical movement. So because it's multiplication or division, we're looking at stretches or shrinks, and we're looking at vertical. So everything on the outside happens the same as what you would think it would. So if we multiply by 1/3, that's actually going to make it shorter. If we multiplied it by 5, it would make it larger by a factor of 5. What this does is it multiplies every y value by 1/3. So for example, this guy that was at a height of 1 is now down here at a height of 1/3. Let's draw it in blue. This guy that was at a height of 0, it's still at a height of 0. This guy that was at a height of -1 is now at a height of -1/3. Still at a height of 0, at a height of 1/3. At a height of 0, at a height of -1/3. At a height of 0. So this blue line is this whole function up here. All of the height values got squished by 1/3 of their normal height. So everything comes in. Now, it can be difficult on a graph to see, is this a vertical shrink or a horizontal compression? Okay. The only way to tell is vertical movements, vertical shrinks and stretches, the guys on the x-axis stay the same. So vertical stretches and shrinks, the guys on the x-axis stay. Horizontal, now this works for all types of graphs, not just for the trig functions. Horizontal stretches and shrinks, the only guys that stay the same are the guys on the y-axis. Notice that between here and between here we had a horizontal compression or a horizontal shrink. The only guy that stayed the same was this guy right here. Everything else moves. When we have a vertical issue, the only guys that stay the same are these guys, because they are on the x-axis. Now that's it. That's all you got to do. So this blue graph is the end graph. So what I would do as an instructor is I would give you a function like this, and I would give you 4 blank graphs, and I would ask you to graph it out. Okay? Over that interval, whatever it happens to be. And you need to draw enough for the graph so that I can see at least one whole cycle. You also need to be specific about where you're crossing. It needs to be very obvious where we're crossing. If you don't label your axes, it's not correct. So what we need to do on a test is we need to label both axes. We need to draw it so that it's clear as to where the function crosses. Each point that you have labeled, okay, needs to be very clear how this is running. Okay, if you don't put axes on here and you just start drawing, oh, I'm stretching and shrinking, and you make it a mess, you won't get any points for that. So it has to be just exactly like I'm doing it right here. We draw out, we put some nice dots on here, we know where this guy is, and then we show each movement, each curve as we go through. So now I can erase my green curve here, and we know that the final curve is this blue curve right here. Now I'll also ask you, what are the period? What is the period? What is the amplitude? And what is the phase shift? Now if I ask you from an equation, just like this, starting out with this equation up here, we can do it algebraically, or we can do it by looking at the graph. So the period is how often it takes to repeat itself. Well, clearly the period from here to here, it's repeated itself now. So from 0 to pi, or it took pi to repeat itself. Its amplitude is half the distance between the top and the bottom. Well, it goes from a height of 1/3 to a height of -1/3, so half that distance is positive 1/3, and the amplitude is always positive. The phase shift is how far do we move left or right. Now the phase shift is a little bit harder to see, so what we do is we take an original point and we see where it moved to, and the best point to use is your point that is right on the x-axis and the y-axis, the origin. Take this point. That point first moved to the right by pi/2. Then it moved back to pi/4. And then it stayed where it was. So the overall movement, the end movement, is to the right, so do positive pi/4. If you want to say pi/4 to the right, you can. If you want to say to the left, you either make this negative or say to the left. That's how we can do it from the graph. I may give you just a graph on the exam and ask you period, amplitude, and phase shift. Or I may show you a sequence of graphs and have you figure this out. So don't rely on just algebra. Now the algebra tricks that I'm going to show you right here work if you have the equations. So let's say we have this equation like this. Well, the period is found algebraically by taking the normal period of sine. So let's just quickly discuss the normal periods. Sine, cosine, secant, and cosecant. Their normal periods are 2 pi. We discussed that the first night. We looked at the graphs of each of those, and we said each one of these takes 2 pi to repeat itself. The only ones that don't have a normal period of 2 pi are cotangent and tangent. These guys repeat themselves every pi. So to find the period, you take its original period and you divide it by the number in front of your variable. And so you notice that we got the same value. The amplitude is found by taking the absolute value of the number out here. And so that's 1/3. So that gave us the same value there. And then the phase shift, that is found by taking the back number and dividing it by this number. So pi over 2 divided by 2, that's the same as pi over 2 divided by, multiply by 1/2, which is pi over 4. So we get the same number there. So you'll be asked to take a graph, step by step, draw out, explain what's going on. Okay, you can write things down in words like I did, tell me what you're doing, make sure it's obvious that I know where your points are going. Okay. You'll have to label your axes correctly, everything's got to be nice and neat. Okay. You'll have to do all of that without a calculator. I would expect you to be able to find the period, the amplitude, and the phase shift just from looking at the graph. So there might be a case where I don't give you the equation, I just give you the graph, and I expect you to find these. Now the phase shift's the hard one because you got to know where you originally started, so I'd have to give you a series of graphs just like we had here, and I would do that. I can also ask you to find the amplitude, period, and phase shift from a given function algebraically, and this is how we do it over here.